Find the stress in the compression steel Fs prime in pounds per inch squared. In this problem, we are provided with a cross-section of a doubly reinforced concrete beam. The dimensions for the height, depth to tension steel, D, and depth to compression steel, D prime, are provided. The yield stress and Young's modulus of the steel are also provided, as well as the strain in the tension steel, epsilon s. For doubly reinforced concrete beams, the prime term refers to the steel in the top of the beam, which is the steel in compression. The stress in the compression steel, Fs prime, equals the strain in the compression steel, epsilon s prime, times the Young's modulus of the steel, Es. We already know the Young's modulus of the steel equals 2.9 times 10 to the 7th pounds per inch squared. So all we need to determine is the strain in the compression steel. From strain compatibility, we notice the strain in the compression steel can be determined using similar triangles. If we define the length C as the depth to the neutral axis, then the strain in the compression steel is to C minus D prime as the strain in the concrete is to C. If we isolate the strain in the compression steel, we get the strain in the compression steel equals the strain in the concrete times C minus D prime, all divided by C. The strain in the concrete at failure is taken to be 0.003, and we know the depth to the compression steel, D prime, equals 3 inches. But we don't yet know the depth to the neutral axis, C. To find C, we can use similar triangles again, but this time involve the strain in the tension steel term, epsilon s, where epsilon s is to D minus C as epsilon C is to C. Solving for the length C, we find C equals the strain in the concrete times D divided by the strain in the concrete plus the strain in the tension steel. From before, we know the strain in the concrete equals 0.003. The problem statement provides the depth to the tension steel, D, equals 20 inches, and the strain in the tension steel equals 0.004. Plugging in all the known variables, the depth to the neutral axis, C, equals 8.57 inches. Now we can solve for the strain in the compressive steel by plugging in 8.57 inches for C, as well as the values for the strain in the concrete, epsilon C, and the depth of the compression steel, D prime. The strain in the compression steel equals 0.00194. If we return back to the beginning of the problem, our equation to find the stress in the compression steel was the product of the strain in the compression steel and the Young's modulus. After plugging in these values, the stress in the compression steel equals 56,260 pounds per inch squared. When reviewing the possible solutions, the answer is B.